Hello students, today we are going to discuss about uncertainties in physics practical. Let us see what are the main sources of uncertainty in a measurement. You can classify the sources of uncertainty into three major categories. One is because of the instrument there could be an uncertainty. For example, zero error in an instrument. The second reason is the person who is taking the measurements. Examples are human reaction time and parallax. Third reason is surrounding conditions like room temperature, air resistance, etc. Now we are going to see each reason in detail. First of all, the resolution of instrument. How resolution of an instrument becomes uncertainty. This is a meter rule. So what is the resolution of a meter rule? Resolution means the minimum interval between readings. The minimum interval in meter rule is 0.1 centimeter. That's called the resolution of meter rule. Another example, if you have a measurement height of an object is equal to 885 millimeters. So what is the resolution of the instrument which you used to take this measurement? How do you find it directly looking at the reading even if you don't know the instrument? Just think about the next measurement. After 885 millimeters, the next measurement will be 886 millimeters. What is the interval between these two readings? That's what you call resolution. So 885 and 886. If you take that differences, it's 1 millimeter. So 1 millimeter is the resolution of the instrument. Another example, given reading is 27.10. So the next reading is 27.11, then 27.12. The interval between two readings is 0.01 centimeter. Now we are going to see how this resolution becomes uncertainty. So let's consider this example. I'm going to measure the length of an object. The length is between 4.1 centimeters and 4.2 centimeters. It's closer to 4.2 than 4.1. But how much do you write as the length? Do you write 4.1 centimeters or 4.2 centimeters? This is what you call uncertainty. So there's a confusion which reading to take. In meter rule, we don't do any additional correction like vernier caliper or micrometer. So in meter rule, always we have to take reading which is closer. So here the reading I should write is 4.2 centimeters, even though it's not exactly 4.2. Now another object length is like this. It's more than 4.2 centimeters, but not exactly 4.2. So now how much do you write as the reading? Since it's close to 4.2, again I have to write 4.2 centimeters. So when you see a reading 4.2 centimeters, it doesn't mean the student got 4.2 centimeters. It means the student could have got anywhere between 4.15 to 4.25 centimeters. This much range of uncertainty is there in the measurement. So there's an uncertainty of plus or minus 0.05 centimeters. Here 0.05 centimeters is half of the instrument's resolution. So this is how resolution of an instrument causes uncertainty in the measurement. This problem occurs with every single instrument because every instrument has a resolution and you can't measure beyond that resolution. The uncertainty in any measurement is equal to half of the resolution of the instrument. All the previous examples we had just one measurement and we took half of the resolution of the instrument as uncertainty because we have to assume the person who is taking the measurement is perfect. But what if you have a set of different readings? Then the uncertainty is not only caused by the instrument but also by the person who took the measurements. Let's see how to calculate the uncertainty if there are different measurements. We are going to find a quantity called half range. Let's see how to calculate the half range. You have to take the highest value out of your measurements, then take the lowest value out of your measurements, then you subtract the highest minus lowest, you will get the range of your measurements, then just find half of that answer. That's called half range. It's how much variation is there from the mean value to the maximum or to the minimum. So half range is considered as the uncertainty if there's a set of different measurements. Now let's see why you need to convert this uncertainty into percentage. So just stating the uncertainty won't give you the exact size of the error that happened in a measurement. For example, you are counting apples. Let's say you counted 1000 apples and you missed one. So there's an error of 1 apple. On another occasion, you counted just 5 apples and again you missed one. In both cases, what is missing is just 1 apple, but is the size of the error same? Missing 1 apple out of 5 and missing 1 apple out of 1000 are not the same size of error. So just by stating uncertainty, you will not know how big is the mistake. For that, you need to convert the uncertainty into percentage. Let's consider another numerical example here. In both cases, meter rule is used. So the uncertainty is the same, but which measurement has a bigger error? Let's see how to calculate the percentage uncertainty. Uncertainty in the measurement divide by what measurement you made multiplied by 100. 0.05 centimeters out of 4.2 centimeters is how much percentage? You will get its 1.2%, but 0.05 out of 94.2, it's just 0.05%. So what you can see here is, even though the uncertainty is same, the percentage uncertainty or the percentage error, it is not same. So in any measurement, what is important is the percentage uncertainty, not just the uncertainty. It's because the accuracy of an experiment depends on the percentage uncertainty. So in order to make an experiment more accurate, you have to decrease the percentage uncertainty. Let's see how to reduce the percentage uncertainty. The most common way of reducing the percentage uncertainty is to increase the size of measurement. As your measurement becomes bigger and bigger, the percentage error in the measurement will become smaller and smaller. For example, in order to find the thickness of a coin, we take like 10 coins. Or to find thickness of one paper, we take 100 papers. That's how you make measurement big, and as a result, the percentage uncertainty becomes very small. So in any question, if they ask how to make an experiment more accurate, always you should think about how to reduce the percentage uncertainty. Now we know how to find the uncertainty and percentage uncertainty. The next part is, how do you combine the uncertainties in different measurements? You will be doing an experiment to find something complex like density, volume, etc. So that would have multiple quantities measured. How are you going to combine the uncertainties in different quantities? There are two scenarios here. One is the quantities are added or subtracted. Second case is the quantities are multiplied or divided. Let's see each case how you're going to combine the uncertainty. Let's take this example. You want to measure the diameter of a coin, but you know the percentage uncertainty will be very high if you take a single coin, since the measurement will be very small. So what I'm going to measure the total diameter of 5 coins in order to reduce the percentage uncertainty. In order to eliminate parallax error, I'm using set squares. These are the measurements I got. Now by subtracting this, I can get the total diameter of 5 coins, that's 12.8 centimeter. What is the uncertainty in this answer? 12.8 plus or minus how much should I write? Uncertainty is not 0.05 centimeters. You cannot look at the decimal places and decide the uncertainty, because 12.8 centimeters is not a measurement. It's a calculated answer. Here the quantities are subtracted to get that answer. If quantities are subtracted or added, what you have to do is add the uncertainties in the measurements. Even if it's a subtraction, the uncertainty, the errors in physics will never get subtracted. It always gets added. When I measured 1.7 centimeters, there will be an uncertainty of 0.05 centimeters. That's half the resolution. Again, when I measured 14.5, there will be 0.05 centimeters uncertainty. This is the case of quantities being subtracted. And if the quantities are being subtracted, the rule is you have to add the uncertainties. So the total uncertainty in 12.8 is plus or minus 0.1 centimeters. Now let's calculate the percentage uncertainty in this answer. The total uncertainty occurred is 0.1 centimeters when you got the value 12.8. So the percentage uncertainty is 0.1 divided by 12.8, then multiplied by 100. The answer is 0.8%. What if you measured just one coin diameter directly? Then how much error will be there? Here also there are two measurements. I am subtracting both measurements to get the diameter, that is 2.6 centimeters. The uncertainty is still 0.1 centimeters. If you calculate the percentage uncertainty, you will see the answer is 4%. Means when you used 5 coins instead of 1, the error decreased about 5 times. This is the advantage of making the measurement big. The same rule of adding uncertainties goes for quantities multiplied by a numerical constant like 2, half, etc. So let's see this example. A student measured the diameter of a coin with an uncertainty of 0.04 millimeters. Now the student is going to calculate the circumference. Equation is given pi d, it's same as 2 pi r. The circumference is 5.34 millimeters. Now the question is, what is the uncertainty in this answer? Is it same as 0.04? No. Since the quantity is multiplied by pi, the uncertainty also should be multiplied by pi. Pi times d is like adding d pi times, like 2d means d plus d. And when you add the quantities, the uncertainties also should be added. So you'll get pi into 0.04, that is 0.13 millimeters. So if the quantity is multiplied by a numerical constant, the uncertainty also should be multiplied by the same numerical constant. Now let's see how to find the percentage uncertainty in the value for circumference. Uncertainty always exists in the original measurement. So always the best method is to use the measurement. Here it's the diameter. So you can do the uncertainty in diameter divided by the value of diameter multiplied by 100. Answer is 2.4%. The same thing you can calculate using the value of circumference and its uncertainty. What you can understand from here is the percentage uncertainty will not change if there is a constant in the equation. Means the percentage uncertainty in diameter or percentage uncertainty in circumference is just the same, but their uncertainty will be different. Second case of combining uncertainties is if the quantities are multiplied or divided. I am given distance and time and asked to calculate velocity. I got the velocity 0.36 meters per second. Now, how much uncertainty is there in this answer? Like plus or minus how much meter per second should I write? This is a case of quantities are divided. If you try to directly add the uncertainties, it won't make any sense because you can see the units. 0.2 centimeters you cannot add with 0.03 seconds. In addition or subtraction, the units will be exactly the same. But in multiplication or division, any quantities can be multiplied or divided. So here you cannot directly add the uncertainties. You need to find a common unit for error, and that common unit is percentage. So both uncertainties you have to convert to percentage uncertainties, then add. Again, it's always addition whether the quantities are multiplied or divided. This is the total percentage uncertainty in velocity. So directly you won't get the uncertainty. You will get the percentage uncertainty. Means you can write 0.36 meter per second plus or minus 4%. If you want the uncertainty, like how much meter per second that is, you can easily convert it. Just find what's the 4% of 0.36. Now you can write 0.36 plus or minus 0.01 meter per second. If the quantities are multiplied or divided, you will never get the uncertainty directly. First, you will get the percentage, then you can convert to uncertainty. Here is another example. You're finding acceleration. So let's convert each uncertainty into percentage. What you can see is there's a t square, means t multiplied by t. So the error in t will be added 2 times. That is the percentage uncertainty in distance plus 2 times the percentage uncertainty in time. You don't need to consider the numerical 2 when you find the percentage uncertainty. So this is the total uncertainty in acceleration. And if you want the uncertainty, you can convert the percentage. Now we will see a special case of adding errors. What if there is an addition as well as multiplication of quantities in an equation? Let's take this example. All the values are given. At first, I am finding the original value of A without any uncertainties. Now we are going to calculate the uncertainty in A. The problem is, first part of the equation is a multiplication. So you have to add the percentage uncertainties, and the answer you will get for first part error will be in percentage. The second part of the equation is minus d, which is a subtraction. So you have to add the uncertainties and cannot use percentage. So let's see how to solve this. At first, calculate the percentage uncertainty in B into C. So the total error in B into C is 1.7%. Now the problem is the next part is a subtraction. So by rule, you have to add uncertainties in the terms B into C and D, not percentage. So you have to convert percentage uncertainty in B into C to its uncertainty. Just multiply 1.7% with the value of B into C. The value of B into C you have to calculate, that is 5.32 centimeters squared. And the uncertainty in that value is 0.09 centimeters squared. Now you can directly add 0.09 plus the uncertainty in D, which is 0.02, to get the total uncertainty in A. This method might be long in some cases, so I will show you another method. In this method, we are using a concept I told at the beginning, that is uncertainty in a value equals the half range. In this method, you have to calculate the maximum and minimum values of A, then find the half range. I am finding maximum value of A. For that, I have to take highest value of B, the highest value of C, and the lowest value of D, since D is subtracted. So if there's a subtraction, you have to use lowest value so that the answer for A will be the highest. So highest value of A is 2.89 centimeters squared. Just do the opposite to find the lowest value of A. Use the lowest value of B and C and the highest value of D so that the answer for A will be smallest. That is 2.68 centimeters squared. Now that you got highest and lowest values of your answer, just find the half range, and that will be the uncertainty. This second method is more useful if the equation is complex, like this example. In order to get highest value of P, you have to put highest values of quantities in the numerator and the lowest values of the quantities in the denominator. Value of H should be lowest since it's subtracted. In order to get lowest possible value of P, you have to put lowest values of B and D since they are in the numerator. In the denominator, you have to put highest value of C. H value also should be the highest. Once you get lowest and highest values, just find the half range. That will be the uncertainty in P. We have seen how to combine the uncertainties. Now we are going to see what is the use of calculus. The ultimate use of finding errors is to make conclusions about the result, whether your answer is valid or not. So there are two methods for doing this. One method is to find the maximum and minimum possible values of your answer and see if the actual value or the standard value is between your maximum and minimum values. The second method is to calculate a new quantity called percentage difference. I will talk about that later. First example, a student is given an object. He measured the length, breadth, thickness and mass of the object, then calculated the density of the material, and he got 2630 kilograms per meter cube. He also has calculated all the uncertainties in all the measurements, converted to percentage uncertainties, and finally got 5.6% as the total percentage error in the experiment. Now, the question says the standard value of density of aluminum is 2750. The question is to check whether the object the student got is made of aluminum or not. You know, the values 2630 and 2750 does not match. But you can't make a conclusion directly because this might be due to the uncertainties in the measurements. So you need to consider the total errors happened in the experiment. In the first method, we are going to find the maximum and minimum possible values of the student's answer. For that, first you have to find the uncertainty. What is given is percentage uncertainty. So I'm going to convert the 5.6% into kilogram per meter cube. So what is 5.6% of 2630? That is 147. This is the uncertainty in the density value obtained by the student. That means the density obtained by the student could go plus 147 above the value 2630. It could also go 147 below from 2630. I'm going to find the maximum and minimum possible values by subtracting and by adding the uncertainty. The actual value 2750 is well inside the range of uncertainties. So if the actual value comes anywhere in between the maximum and minimum possible values of student's answer, then the student is correct. The student here has got aluminum. Now we are going to see the second method, which involves percentage difference. Let's see how to find the percentage difference. Take the higher value among your value and the standard value, then subtract the lower value, then divide by the standard value, then multiply by 100. This answer will give how much variation is there between your value and the standard value in percentage. Answer is 4.4%. Now compare this answer with the total percentage uncertainty in the experiment, which is 5.6%. If the percentage difference is less than percentage uncertainty, then your value is valid. Means the difference is justified with the uncertainties. If the percentage uncertainty is less than the difference, then your result is not valid. A special case is if there's no standard value given. Here the student is given two different samples, may be made of different materials. Student found the density of each material and the percentage error in each experiment to get the density. Now we are checking whether these two materials are the same. So I'm finding bigger value minus smaller value, then divide by average of these values since there is no standard value here. 6.7% variation is there between the values. Now what you are going to check is what is the total percentage error. For getting the first density, there was an error of 1.9%. Then there is 2%. For the second density, the total is 4% error. Now we are going to check whether this 4% error can justify 6.7% difference. No, the difference is much bigger than the error. So what you conclude is they are not actually the same material. You can see another example here. The standard values of Young modulus of three different metals are given. A student is given a particular object and he calculated the Young modulus of the material. He got 42.1 gigapascal with a percentage uncertainty of 6%. The question is whether he can identify the material which he was given. So here the easiest method is the range method. First, convert the percentage into the uncertainty. I got 2.53 gigapascals. This means student's value can go plus 2.53 or minus 2.53. I am finding the maximum and minimum possible values. Any value between this maximum and minimum are correct values. But here the problem is two of the given values are coming inside the range. So the conclusion is the student cannot confirm which material he was given. So that's all about uncertainty. Before ending the video, I will show you the definitions of some of the important terms used in the video.